Welcome to Relearn, where complex ideas meet simple explanations. Today, we are diving into quantum mechanics, perhaps the strangest, most mind-bending theory science has ever produced. It is not just abstract math or thought experiments. Quantum mechanics powers everything around you, from the phone in your hand to the light entering your eyes. Everyone has heard the word quantum, but what exactly does it mean? In this video, we will explain quantum mechanics in the simplest way possible. But why is quantum mechanics so counterintuitive? It is because our brains evolved to understand the everyday world, things we can see, touch, and directly experience. We are wired to think in terms of objects that are either here or there, moving or still, existing or not existing. We created mathematics to make sense of patterns in nature. Quantum mechanics required us to completely reimagine how reality works. Why did scientists create quantum mechanics? Classical physics explains everyday objects, but it fails for tiny particles like atoms and electrons. Experiments showed that to understand these, scientists had to accept strange, revolutionary ideas that challenge common sense. To explain quantum mechanics simply, we will use the example of a particle trapped in a one-dimensional box, the simplest quantum system. Imagine you have a tiny particle, like an electron, trapped between two walls that it cannot pass through. According to classical physics, this particle could have any amount of energy, move at any speed, be found anywhere inside the box with equal probability, behave like a tiny bouncing ball. But quantum mechanics tells us something completely different. To understand this, we need to dive into the mathematics that governs quantum systems. You can skip math part if you feel uncomfortable. The heart of quantum mechanics is the wave function, usually written as psi, the Greek letter psi. The wave function is a mathematical description that contains all the information about a quantum system. Think of it as nature's way of keeping track of every possible state the particle could be in. The wave function itself is not directly observable. What we can observe is psi square, the square of the wave function, which gives us the probability density of finding the particle at any location. The Schrödinger equation, H psi equals E psi, where H is called Hamiltonian operator, psi is wave function, and E is energy. Erwin Schrödinger, inspired by de Broglie's idea of matter waves, developed the Schrödinger equation to describe how quantum particles behaves like waves, and this equation became core part of quantum mechanics. The wave function must satisfy the Schrödinger equation, which for our particle in a box looks like h/square upon 2m times d square psi upon dx square equals E psi. Let us break this down. H/ equals reduced Planck's constant, h upon 2 pi. M equals mass of the particle. D square psi upon dx square equals second derivative of the wave function. E equals energy of the particle. Psi is wave function of particle. Why the second derivative? The first derivative, d psi upon dx, tells us how the wave function is changing at any point, its slope. The second derivative, d square psi upon dx square, tells us how that change is changing, the curvature of the wave. In physics, the second derivative is connected to kinetic energy. Just like in classical mechanics, where kinetic energy relates to acceleration, which is the second derivative of position, in quantum mechanics, the kinetic energy operator involves the second derivative of the wave function. The more curved the wave function, the higher the kinetic energy. A completely flat wave function has zero kinetic energy. Solving the equation. Now, let us solve this step by step. We can rearrange the Schrödinger equation. D square psi upon dx square equals minus 2m e upon h/square times psi. Let us call k square equals 2m e upon h/square. So, d square psi upon dx square equals k square times psi. This is a classic differential equation whose solutions are sine and cosine functions, because they are the functions whose second derivative is proportional to the negative of the original function. The general solution is psi x equals a sine kx plus b cos kx. But our particle is trapped in a box from x equals 0 to x equals L, and it cannot exist outside the box. This means psi 0 equals 0. Particle can't be at the left wall. Psi L equals 0. Particle can't be at the right wall, since particle cannot exist outside wall. Psi 0 equals 0. Psi L equals 0. Applying psi 0 equals 0. A sine 0 plus B cos 0 equals A. 0 plus B 1 equals
B
equals
0.
So B equals 0. And our solution becomes psi x equals A sine kx. Applying psi L equals 0. A sine kl equals 0. Since A is not equal to 0, otherwise the particle would not exist, we need sine kl equals 0. This happens when kl equals n pi, where n equals 1, 2, 3. Therefore, k equals n pi upon l. The final solution. Our wave functions are psi x equals a sine n pi x upon l, where a is determined by normalization, ensuring the total probability equals 1. Solving the integration 0 to L psi squared dx equals 1. We get A equals under root 2 upon L. So, psi x equals under root 2 upon L sine n pi x upon L. Energy quantization. Remember k square equals 2 me upon h bar square and k equals n pi upon L. So, square of n pi upon L equals 2 me upon h bar square. Solving for energy. E equals n square pi square h bar square upon 2 ml square. This is why energy is quantized. The boundary conditions force the wave to fit perfectly in the box, which only allows specific wavelengths, which correspond to specific energies. Physical interpretation. N equals 1. Ground state, lowest energy. Half a sine wave fits in the box. N equals 2. First excited state. 1 complete sine wave fits in the box. And so on. The particle exists as a standing wave, and the probability of finding it at position x is psi square equals 2 upon L, sine square, n pi x upon L. What this means? This simple example reveals the heart of quantum mechanics. 1. Quantization. Energy, angular momentum, and other properties come in discrete packets. 2. Wave-particle duality. Matter behaves as both waves and particles. 3. Probability. We can only predict the likelihood of outcomes, not exact results. 4. Uncertainty. There are fundamental limits to what we can know about a system. Comparison of classical versus quantum model of particle in a one-dimensional box. Classical. Particle can have any value of energy. Move at any speed. Can be found anywhere in box. Equal probability of finding anywhere in box. As per quantum mechanics, can have only certain energy values. Probability of finding particle not equal at all places. Can be present at two places at the same time. Conclusion. Nature at its fundamental level is probabilistic, not deterministic. At its core, nature works by chance and not by fixed rules. And this is not because we can't measure, it is a fundamental property of nature. Quantum mechanics is the most weird theory ever developed, but it is the most successful theory in science, explaining the universe at its smallest scales. It can explain why atoms are stable, how chemical bonds form, and powers tech like lasers, computer chips, and MRI machines. Thanks for watching this video. As we have seen, reality at its core is far stranger than we can imagine. To sum it all up, here is a quote from Niels Bohr, the famous scientist. Everything we call real is made of things that cannot be regarded as real.